Hi guys, in the previous lecture we have covered the power calculation in AC circuit and we have solved some problem based on that. In today's lecture we will be starting series resonance. Okay, so before starting series resonance I would like to tell you about the quality factor. What is quality factor? Generally quality factor is denoted as Q, which is given by 2 pi into maximum energy stored upon energy dissipated in one cycle. Okay, or in other word we can say that ratio of energy stored to energy dissipated in one cycle. So what is the significance of quality factor? Why we are finding quality factor? In any circuit we want losses as minimum as possible, so energy stored must be high as compared to energy dissipated. So quality factor gives an idea how much energy is stored in any circuit with respect to energy dissipated. So in any circuit we want losses as minimum as possible, so energy stored must be high as compared to energy dissipated, hence quality factor should be as high as possible. Okay, in other words quality factor can be represented as ratio of reactive power upon active power. So let us consider one series RL circuit. If I have to find the quality factor of series RL circuit, that is given by ratio of, this is quality factor QU represented as QU, ratio of reactive power upon active power. And in a series RL circuit, what is the reactive power? The reactive power can be calculated by I RMS square into XL upon I RMS square into R, that is equal to XL upon R, that is equal to omega L upon R. In this way we can calculate the quality factor of any kind of circuit. Okay, there is also one term known as dissipation factor. What does dissipation factor means? The dissipation factor is nothing but 1 upon quality factor. Okay, means how much power is dissipated in one cycle with respect to how much energy is stored, that is the dissipation factor. Okay, now let us find the quality factor of each and every series circuit. So if I will talk about the purely resistive circuit having current IRMS is equal to R, then quality factor is equal to reactive power upon active power. So reactive power for purely resistive circuit will be 0 and active power will be I square R. So I will get quality factor is equal to 0. If I will talk about the purely inductive circuit, then the quality factor of purely inductive circuit is given by I RMS square into XL upon I RMS square into R. Since the resistance of purely inductive inductance is equal to 0, so quality factor will be infinite. If I will talk about purely capacitive circuit, then quality factor will be I RMS square into XC upon I RMS square into R, which you will get infinite because the resistance of purely capacitance is 0. If I will talk about the RL series circuit, then I will get quality factor is equal to omega L upon R. If I will talk about RC circuit, then I will get the quality factor is equal to I RMS square into XC upon I RMS square into R, that is equal to XC upon R, that is equal to 1 upon omega CR. If I will talk about the quality factor of RLC circuit, which we will derive in the next slide, then the quality factor you will get that is equal to at resonance, that is equal to omega L upon R, that is equal to 1 upon omega CR, and in other word we can represent 1 upon R under root L by C. This I will derive in the next slide, no problem. Now let us consider the parallel RL network. If the network is like this, then how will I find the quality factor? Quality factor is the reactive power, ratio of reactive power upon active power. So reactive power I will get V square upon XL upon V square upon R, since the voltage across both the resistance and inductance are same, that's why I am taking power in V square upon XL and V square upon R. So finally I will get R upon XL, just exactly opposite to what we have found in series RL circuit. Okay, if I will talk about the parallel RC circuit, then quality factor will be V square upon XC upon V square upon R, that is equal to omega C R. This will be R upon omega L, and this parallel RL, the quality factor of parallel RC circuit is exactly opposite to the quality factor of series RC circuit. If I will talk about the parallel RLC circuit like this, then I will get quality factor is equal to R under root C by L, which is exactly opposite to the series RLC circuit. Okay, so in this way we can easily find the quality factor of different series and parallel circuit. Now we know that dissipation factor is equal to 1 upon quality factor, so we can find the dissipation factor also, like dissipation factor is equal to 1 upon Q. Okay, now let us move to understand the series resonance. Let us consider a series RLC circuit connected with voltage V, that is AC voltage. The voltage drop across RLC is VR, VL and VC respectively. Okay, now the impedance of this circuit is given by R plus j omega L plus 1 upon j omega C, and we know that under resonance condition magnitude of XL is equal to magnitude of XC. That is, this I have already explained you in lecture number 21 when I have explained you the phasor diagram of RLC network. That means put XL is equal to omega L, that is equal to 1 upon omega C. So finally you will get omega naught, that is the resonant frequency, that is equal to 1 upon under root LC in radian per second. So F naught will be 1 upon 2 pi under root LC. So under resonance condition, this omega L is equal to omega C, 1 upon omega C. So the Z, that is the impedance, will be purely resistive, right? And current is equal to V upon Z. Since Z is minimum, so current will be maximum under resonance condition because Z is equal to R. Okay, so under resonance condition the impedance offered in the circuit is purely resistive, which is minimum, so the current flowing in the circuit will be maximum, and under resonance condition the inductive reactance is equal to capacitive reactance, or in other word we can say that the voltage drop across inductor and capacitor are equal. Okay, so if I will plot the impedance versus frequency, then I will get the waveform like this. Initially at low frequency the impedance is high, and when we will increase the frequency then the impedance will become low, and at resonance frequency the impedance will be minimum, that is equal to R, and with further increase in frequency the impedance will increase. Okay, so at high frequency this XL term is greater than XC term. If you will put the frequency very high, then this XL term will be greater than XC term. So at high frequency the inductive reactance is greater than capacitive reactance. XL is greater than XC. So we can say that the overall circuit will behave like a lagging load. Why? Because XL is greater than XC, means the overall circuit will behave like an lagging circuit. Now at low frequency the XC will be greater than XL. Here XC will be greater than XL. So this will be leading power factor and this will be lagging power factor. Now at resonance frequency the impedance I am getting, that is purely resistive in nature. That means the network will behave like an purely resistive circuit, and in purely resistive circuit we know that the angle between voltage and current is 0, so power factor will be unity. So at resonance it will give unity power factor. Okay, now tell me, what at resonance what is the value of VR? See, VR is equal to I into R, and at resonance we know that I is equal to V upon R into R, that means V. So at resonance condition, the voltage drop across resistor is nothing but the supply voltage. Okay, now tell me, what is the voltage drop across inductor at resonance? VL is equal to I into XL, that is written by I into J omega L. And at resonance we know that current is maximum and impedance is minimum, which is equal to resistance. So I is equal to V upon R into J omega L. Now we know that omega L upon R is nothing but quality factor, which we have derived in the previous slide. So finally I will get J Q V. So voltage across inductor V is nothing but product of quality factor multiplied by supply voltage. Okay. Similarly, VC can be found by VC is equal to I into XC, and at resonance I is can be replaced by V upon R, and XC can be replaced by minus J upon omega C, and we know that 1 upon omega CR is nothing but quality factor, so we can represent like this J Q V. So at resonance we are getting magnitude of Vc is equal to magnitude of VL, which we know earlier that the voltage across inductor and capacitor are same, and that is equal to QV. Okay, where Q is the quality factor and V is the supply voltage. Got it? Now let us define one more term, that is known as bandwidth. What do you mean by bandwidth? So bandwidth is a range of frequency for which our signal exists. It is a range of frequency for which our signal exists. Actually, the signal exists from 0 to infinite frequency. If I will plot the current waveform of any signal with respect to omega, then I will get the graph like this. So this signal exists from 0 to infinite frequency, but we have to define the band of frequency in which the signal is significant strength. Otherwise, what will happen? We won't be able to define other signal, and we won't be able to generate other channel like in radio. So that set of frequency for which the channel has a significant strength is called bandwidth. So we want the bandwidth of the signal as small as possible, so that more channel can be generated in less frequency range. Suppose the frequency range is from 0 to 100 kilohertz. Okay, and I want to insert 10 radio channel in between 0 to 100 kilohertz, means I have to give 10 kilohertz of bandwidth to each channel. Then only I can generate 10 channel within the range of 100 kilohertz. Okay, suppose I have given 100 kilohertz to one channel, means in between 0 to 100 kilohertz we have only one channel present. So bandwidth will be 100 kilohertz, which is more than the previous one. That's why we want the bandwidth of the signal as small as possible, so that more channel can be generated in less frequency. So how do we limit bandwidth? What are the criteria for limiting the bandwidth so that more channel can be generated in less frequency range? For that we limit bandwidth such as, if power of any signal is equal to 1 by 2 of maximum power, then signal loses its strength. We limit the bandwidth like this, means if any signal having power greater than half of the maximum power, then that signal will be generated, otherwise it will lose its strength. Means in order to find the cutoff frequency, let us suppose for a series RLC circuit, we have seen the impedance graph is like this. So current graph will be like this, just opposite to the impedance. So we will get maximum current here, and we will get 1 by root 2 times of maximum current like this. So in order to find the cutoff frequency, what I will do? we know that we define limit such that when power will be greater than half of P max, then that channel will exist, and when power will be less than half of P max, then that channel will lose its strength. Okay, so we know that P max is equal to I max square upon R. Okay, now when power is equal to 1 by 2 of P max, that is equal to 1 by 2 of I max square into R, we can write like this: I max by root 2 square into R. That means when the current will be 1 by root 2 times of maximum current, then we can get the cutoff frequency, because for current less than 1 by root 2 times of maximum current, the channel does not exist, and for current greater than 1 by root 2 times of maximum current, the channel exists. So bandwidth we can define by finding the cutoff frequency. So if I will make Im by root 2 parallel line, then it will cut the graph at 2 point. So this is my cutoff frequency omega 1, and this is my cutoff frequency omega 2. So in between the omega 1 and omega 2 channel exists, and for omega less than omega 1 and for omega greater than omega 2, the channel will not exist. So bandwidth can be defined as omega 2 minus omega 1. Got it? Now in order to find the cutoff frequency omega 1 and omega 2, what I will do, I will write like this: when instantaneous value of current is equal to 1 by root 2 times of I max, then I will get omega 1 and omega 2, right? Now under resonance, we know that I max is nothing but V upon R under resonance condition. So we can write like this: 1 by root 2 V upon R, and this is the instantaneous value of current, that is written by V upon Z. Okay, now V will cancel out, so I will get 1 upon Z can be replaced by R square plus omega L minus 1 upon omega C का whole square under root is equal to 1 by root 2 R. So squaring both sides, we will get 2R square is equal to R square plus omega L minus 1 upon omega C whole square. So finally I will get omega L minus 1 upon omega C whole square, that is equal to R square. So here two cases arises. Case number first is when omega L minus 1 upon omega C is equal to minus R, and case number second is when omega L minus 1 upon omega C is equal to plus R. So we will take these two cases in order to find the lower cutoff frequency omega 1 and higher cutoff frequency omega 2. So take case first when omega L minus omega C is equal to minus R. I will get omega square LC minus 1 is equal to minus omega CR, that is equal to omega square plus R upon L omega minus 1 upon LC. This is the quadratic equation. So we will get omega is equal to minus R upon L. Since the frequency is always positive, so I will not take minus 1, I will take only plus 1 under root of R square plus L square plus 4 upon LC upon 2. Okay, hence we can find omega 1, that is equal to minus R upon 2L plus under root of R upon 2L whole square plus 1 by LC. So this is the lower cutoff frequency. Now in order to find the higher cutoff frequency, we will take the case second, that is equal to omega L minus 1 upon omega C is equal to plus R. Again I will get quadratic equation, that is equal to omega square minus R upon L. So finally omega 2 I will get R upon 2L plus under root of R upon 2L whole square plus 1 by LC. In this way we can find the upper and lower cutoff frequency. Now I found omega 1 and omega 2, where omega 1 is the lower cutoff frequency and omega 2 is the higher cutoff frequency. So bandwidth can be defined as omega 2 minus omega 1. So if I will minus the omega 2 with omega 1, then I will get R upon L. So this is the bandwidth for series RLC circuit. Okay, we can represent bandwidth is equal to omega 2 minus omega 1, that is equal to RL, in terms of frequency F2 minus F1, that is equal to R upon 2 pi L. This is the formula for bandwidth. So finally I have got the cutoff frequency omega 1 is equal to minus R upon 2L plus under root R upon 2L ka whole square plus 1 by LC. Similarly for omega 2 is equal to R upon 2L plus R upon 2L ka whole square plus under 1 by LC. Okay, so these two are the cutoff frequency, the formula for cutoff frequency. Now you can see here that if I will take this as A and this I will take as a B, then this will be A and this will be minus B. So omega 1 and omega 2 is equal to what? A plus B into A minus B. Okay, that is nothing but A square minus B square. A square minus B square. So if you will calculate A square minus B square, then you will get 1 by LC, and in series RLC network 1 by LC can be represented as omega naught square. This is the resonance frequency which we derived earlier, right? So product of cutoff frequency is equal to square of resonance frequency, right? So we can write resonance frequency in terms of cutoff frequency like this: omega naught is equal to omega 1 upon omega 1 into omega 2, that is equal to geometric mean of half power frequency. Omega 1 and omega 2 are known as half power frequency because at this frequency the power is exactly half of the maximum power. That's why it is known as half power frequency. And bandwidth is equal to omega 2 minus omega 1, that is equal to R upon L. Got it? We know that bandwidth is equal to omega 2 minus omega 1, and that is equal to R upon L. So I can write like this: omega 2 minus omega 1 upon omega naught, that is equal to R upon omega naught L, that is nothing but 1 upon quality factor Q naught at resonance frequency. Hence Q naught is equal to omega naught upon omega 2 minus omega 1, that is equal to omega naught upon bandwidth. So we can say that quality factor is inversely proportional to bandwidth. So the conclusion of this relation is, narrow the curve, more is the quality factor. See, if the curve of this current graph is narrow like this, then I will get less bandwidth, and if I will get less bandwidth, then the quality factor of that circuit will be high. Okay, and if the curve of this current graph is broad like this, then there I will get more bandwidth. More bandwidth means less quality factor. Got it? So these all formula you have to keep in mind while solving any RLC series resonance circuit. Okay, now there is one more term that is known as selectivity. What do you mean by selectivity? Selectivity is the ability of a circuit to distinguish between the desirable and undesirable frequency. Actually, the most desired frequency is the resonance frequency. Okay, most desired frequency is the resonance frequency. Okay, because at this frequency the current is maximum and we are getting the maximum power. So selectivity is inversely proportional to bandwidth, right? We can say that selectivity is directly proportional to quality factor. Higher the bandwidth, more undesirable frequency, that is less selective. So if we want to understand graphically, then let us take this current and frequency waveform like this. I have one frequency waveform of one RLC circuit like this and second RLC circuit like this. Okay, let us take the maximum current of both the graph is Imax only, right? So at Im by root 2 I will get the cutoff frequency. So for this red curve I will get high bandwidth omega 2 and omega 2. Bandwidth is omega 2 minus omega 1, so it is more. And for black graph I am getting less bandwidth, omega 1 dash and omega 2 dash. So the curve which are having less bandwidth are more selective. Okay, and the curve which have broad graph or having high bandwidth are less selective. So in order to have a more selective circuit, we must have a high quality factor of that circuit. Okay, and that circuit must work at resonance frequency. So finally, what we have derived? We have derived the resonance frequency omega naught is equal to 1 upon 2 pi under root LC, and that is nothing but the geometric mean of cutoff frequency. We define the quality factor, that is equal to XL upon R, that is equal to 1 of XC upon R, and that must be equal to 1 upon R under root L by C. How we are finding this? See, omega naught is equal to 1 by under root LC, right? And we know that quality factor Q naught is equal to XL upon R, that is equal to omega L upon R. Put omega is equal to, at resonance frequency, omega will be omega naught. So put omega naught is equal to 1 by under root LC, you will get 1 upon R under root L by C. Okay, in this way we derive quality factor in 3 formula, and that is equal to 1 upon quality factor which we will get in parallel resonance circuit. That is the next lecture. Okay, similarly we found omega 1, that is known as lower cutoff frequency, also known as lower half power frequency, and omega 2, that is the higher cutoff frequency. These two we have derived. And finally bandwidth is given by omega 2 minus omega 1, that is nothing but R upon L, and if we multiply this R upon L by omega naught and divide by omega naught, then I will get omega naught upon Q naught, where Q is the quality factor. So these all relation you should keep in mind while solving any series resonance circuit. So let us solve some problem based on series resonance circuit. Let us take the first problem. In series RLC circuit, the quality factor is 100. If all the component value are doubled, then new quality factor. We know that this is series RLC circuit and we have quality factor is equal to 100. Now the question is saying if all the component value are double, means if R is equal to 2R, if L is equal to 2L, and if C is equal to 2C, this is 2R, this is 2L, and this is 2C, then the new quality factor will be what? We know that quality factor is equal to omega L upon R, that is equal to 1 upon omega CR, and that is equal to 1 upon R under root L by C. So we will not use this equation, because this equation contains omega and we don't know the frequency, resonance frequency. So in order to find the new quality factor, we have to use this formula, because the question is saying if all the component values are doubled. So new quality factor will be, if you will double this, then 1 upon 2R under root inductor will be 2L and capacitance will be 2C. So finally I will get 1 upon 2R under root L upon C, which is 1 by 2 of Q old, that is equal to 50. So new quality factor will be half of the old quality factor. Got it? Now see the next problem. In series RLC circuit, the power factor at omega is equal to omega L is. We have to find the power factor at omega is equal to omega L, that is the lower cutoff frequency. Omega L is the lower cutoff frequency which we are representing here omega 1. Okay, we have to find the power factor. Now we know that power factor is equal to cos phi, that is equal to R upon Z, and we know that at omega is equal to omega L, that is equal to omega 1, what we are getting, I is equal to Im by root 2, right, which we have seen in earlier. At lower half frequency, the current we are getting, that is equal to 1 by root 2 times of maximum current, and at resonance Im is equal to V upon R, right. So it will be like V upon root 2R. Now we know that I is equal to V upon Z is equal to V upon root 2R. So finally I will get Z is equal to root 2R at resonance. And at omega is equal to omega 1, that is the lower cutoff frequency. So replace this here, you will get R upon Z is equal to cos phi, and now replace Z is equal to root 2R. So R upon root 2R, finally you will get cos phi is equal to 1 by root 2, that is equal to 0.707, and the angle phi is equal to 45. Now tell me whether it is leading or lagging. It will be leading. How I am getting leading? See, at lower frequency, if you will plot the current graph, then you will get current graph with respect to omega like this. Okay, this is my Im by root 2. Okay, and this is the lower cutoff frequency and this is the higher cutoff frequency. So and this is the resonance frequency, that is equal to, here I am getting Imax, and that is equal to omega naught. Okay, now tell me, Z is equal to R plus j omega L plus 1 upon j omega C. So if at higher frequency this omega L term, that is the inductive reactance, is greater than capacitive reactance, so at higher frequency than the resonance frequency, the inductive behavior is more, so this will be lagging, right. And at lower frequency this capacitive reactance is greater than inductive reactance, so capacitive behavior will be more. So at lower frequency less than resonance frequency, the capacitive behavior will be more, so this will be leading. So at omega is equal to omega 1, the power factor will be leading power factor, and at omega is equal to omega 2, that is the higher cutoff frequency, the power factor will be lagging in nature. Okay, also we have to find the power factor at omega is equal to omega h, that is the higher cutoff frequency. So at higher cutoff frequency also you will get same power factor. At higher cutoff frequency cos phi is equal to R upon Z, and at higher cutoff frequency you are getting the current, that is 1 by root 2 times, so overall you will get 1 by root 2 only, that is equal to 0.707, but this will be lagging, right. So phi will be 45 degree lagging, means inductive behavior is more than the capacitive behavior at higher cutoff frequency, and capacitive behavior is more than inductive behavior at lower cutoff frequency. Okay, now let us solve the next problem. A series RLC circuit has R is equal to 50 ohm, L is equal to 100 microhenry, and C is equal to 1 microfarad. The lower half power frequency of the circuit, we have to find the omega L, that is equal to omega 1. We know the formula of lower cutoff frequency, that is omega 1 is equal to minus r upon 2l plus under root r upon 2l का whole square plus 1 by LC. So if you will put the value of r LC, you will get, so after solving this circuit I will get omega 1 is equal to 19258.24 radian per second. That is given by 2 pi f1, that is equal to 19258.24 radian per second. So f1 is equal to 3.065 kilohertz. That is the lower half power frequency. Okay, you can check it by calci. There may be the calculation mistake, but the concept would remain same. Got it? Now let us take the last problem. A series RLC circuit, when excited by 10 volt sinusoidal voltage, this is series RLC circuit, and 10 volt sinusoidal voltage is given to RLC circuit of variable frequency, exhibit resonance at 100 Hz. I have given resonance frequency that is equal to 100 Hz and has a 3 dB bandwidth of 5 Hz. 3 dB bandwidth means, what do you mean by this 3 dB bandwidth? This is nothing but this is omega 2 minus omega 1 or f2 minus f1, that is given by 5 Hz. Okay, now I have to find the voltage across inductor L at resonance. At resonance, what will be the voltage across inductor L? I have derived one expression, that is quality factor is equal to omega naught upon omega 2 minus omega 1, right? See this formula, Q naught is equal to omega naught upon omega 2 minus omega 1. We can write here also Q naught is equal to omega naught upon omega 2 minus omega 1, where omega naught is the resonance frequency. So quality factor is equal to omega naught upon omega 2 minus omega 1. We can write like f naught upon f2 minus f1. What is f naught? F naught is the 100 and f2 minus f1 is the 5. So I am getting quality factor is equal to 20. Now I have also derived the voltage across inductor at resonance is equal to Q times of supply voltage. So 20 multiplied by 10, that is equal to 200. So that's all about this lecture. In the next lecture we will see parallel resonance, in which we will define quality factor, bandwidth and selectivity of parallel resonance, and we will solve some problem based on that. If you guys understood the concept, then please like this video and subscribe to this channel. For doubt solving, you can join our Facebook group. Thanks for watching this video.